So this is 5.3. We're going to be working on double integrals in polar coordinates. I would say it's a shorter section, although some of the later examples get pretty long. And then the next section is the examples are super duper long when we go over triple integrals. But we will get through it together. So there is a definition here that I recommend you write down if you are someone who takes written notes. We're going to kind of use that. You'll see that the first example here says sketching a polar rectangular region. Sketch the polar rectangular region, and then it gives you a region. So I'm going to show you the figure in a moment, and then we'll talk about it. So kind of nice that our answer gets to be kind of done already. What you're going to be able to tell from here is that we have an R, a little r equal to 1, and a little r equal to 3. And they are the circles of radius 1 and 3, and then also you have it between 0 and pi. So it basically covers the top half of the plane. So the region R is going to look like a semicircle. It kind of looks like a donut or a tire cut in half, right? So finish over here, and we're happy. Okay, everybody loves donuts. Okay, all right. Next problem. It says evaluating a double integral over a polar rectangular region. Evaluate the integral given to us. Okay, so the first thing you want to do is sketch a figure that's going to look similar to the one we just saw, except what's the difference going to be? The outer one, instead of it being, so just be very, very rough. So that's your inside one, where r equals 1. And then you would have another one where r would equal 2. There you go. I don't think you need to go any more detailed than that. So from the figure, what we know is that we would rewrite our region 3x dA. That's going to become 0 to pi and 1 to 2, 3r cosine theta r dr d theta. Okay. So we're using an integrated integral with the correct limits of the integration based on the fact that we are dealing with polar rectangular kind of realm. So if we do the first part, we'll have the cosine of theta r cubed from 1 to theta, and then you get 0 to pi 7 cosine theta d theta is going to become 7 sine theta from 0 to pi, which is going to leave you with an answer of just 0. So in that problem, we integrated with respect to r first. All right. All right, so evaluating a double integral by converting from rectangular coordinates. So we want to evaluate the integral. It's given where R is a unit is the unit circle on the XY plane. So if the region R is the unit circle, then what we can describe that as is that the region for R comma theta would be 0 R to 1 and 0 theta, oops, sorry, to 2 pi. Okay, using the conversions x equal to R cosine theta and y equal to R sine theta. And then we know that dA would be equal to R dr d theta. Then that's going to give us the following. I think you guys can rewrite this part if you want. I'm going to save us a little bit of room. So it's going to go from 0 to 2 pi, from 0 to 1. And it's going to be 1 minus R squared, R dr d theta. And then if you do the first step, you're still going to be 0 to 2 pi, 0 to 1. And it'll be R minus R cubed dr d theta. So 0 to 2 pi R squared over 2 minus R to the 4th over 4. It's going to be 0 to 1 d theta, which is 0 to 2 pi 1/4 d theta, which is just pi over 2. Okay. All right, so this one is saying that we have this double integral, and then this is our region. So we can see that the region is going to be an annular region that can be converted to polar coordinates and described as the following. So I'm going to translate it and then I'll show you the graph. So we know that we can do R is equal to R theta, not 1 R 2. And then we know that we're going to have pi over 2 theta 3 pi over 2. I'll show you this lovely little. Okay. So it kind of looks like the other side of that donut in a way. The partial top and then starting at the bottom. All right, so again, we want to use those conversion ideas that we know about. So, if x is equal to R cosine theta and y is equal to R sine theta, and we have dA equal to R dr d theta. Then you would start with your rewrite, and then you're going to go from pi over 2 to 3 pi over 2, and then 1 to 2, and then you're rewriting it, so it's going to be r cosine theta plus r sine theta, r dr d theta. And then what you can actually do here is you can split them. You'll end up with 1 to 2 r squared dr plus, or sorry, times pi over 2, 3 pi over 2 cosine theta plus sine theta d theta. And then if you do each one, you end up with r cubed over 3, 1 to 2, and then sine theta minus cosine theta pi over 2, 3 pi over 2, which is going to equal to negative 14 over 3. Okay, so a lot of it for this section is going to just be rewriting it into the rectangular coordinates and solving. So there's another definition. There's another problem. And then, so here's what the idea is that you're working with. Again, rewrite. Well, they kind of rewrote it for you. You can start there though. And then we're going to split it. So I'm going to start at split. So you work some stuff on, you end up with 1/4 outside, and then it's going to be 0 to pi, and then r to the 4th, 0 to 1 plus cosine theta, sine theta, d theta. 1/4 is 0 to pi, and then 1 plus cosine theta to the 4th sine theta d theta, which will give you a negative 1/4, 1 plus cosine theta to the 5th over 5, 0 to pi. So then that just gives you 8/5. Okay. I'm sensing maybe we'll be able to get it done early tonight. That is my hope. I don't know how many slides are in the next section though. All right. All right, so the next idea we're dealing with is finding a volume using double integral. So find the volume of the solid that lies under the paraboloid and above the unit circle on the plane. So you can see that figure is given. So what we're going to do is, by the method of double integration, we're going to see that the volume is integral in the following form. So I'm going to write this part down here because then we'll write to the right. Okay. So that should look pretty familiar to you guys. And if we go back a couple of slides, then that should look pretty familiar to you. Example 5 is that 29, I think. So if we go back, oops, yeah. So example okay. So we really don't have to do anything else. All you have to do then is say volume is pi over 2 units cubed. Now, obviously, if you want, you can rewrite it. If this was a problem on a test, you wouldn't be able to just say, well, example 526 had it. So you would still need to know how to do it, but we're just showing an example here where we already have that portion written out, okay? That's how you would want to write it. All right. Okay, so this one's saying finding a volume using double integration. Find the volume of the solid that lies under the paraboloid and above the disk on the XY plane. See the paraboloid in the figure intersecting the cylinder above the XY plane. Okay, so first change the disk, the polar coordinates. So expanding the square term, you're going to have the following. So the first thing we have to do is figure out your polar coordinates. So you're going to have x minus 1 squared plus y squared equals 1. You're going to want to expand the square term, so you're going to get x squared minus 2x plus 1 plus y squared equals 1. Then you want to simplify that, and you're going to end up with x squared plus y squared equals 2x. So if we convert that then to polar coordinates, you're going to end up with r squared equals 2r cosine theta. And then from there, you're either going to have r equal to 0 or r equal to 2. Cosine theta, sorry. Similarly, we're going to do the same thing to the paraboloid. What you're going to end up noticing is that you're going to have z is going to equal to 4 minus r squared. So you would be able to redefine that disk as the following. I'll put it kind of like this. So D is going to be r comma theta. That is a theta. And it's going to be from 0 to pi, and then 0, oops, stop it. Yeah, I think that's okay. And then it's going to be 0, stop. Why won't you let me write? All right, that's just very annoying. Wait, whatever. Over there, and let it be happy. It's on the world. Okay, so you're going to end up with the r comma theta, and it's going to be 0 theta to pi, and then 0 r to 2 cosine theta. Okay. Then we need to dive into what the actual volume is going to look like. That is going to be so the volume okay. Now I'm gonna try to get this all in on one slide. We do have the room this time, unlike some of the ones last time. So then 4 minus r squared r dr d theta. I don't know what's going on with the slides, but okay. So we're gonna have 0 pi 4 r squared over r. No, sorry, over 2. I was right. Minus r to the 4th over r. 0 to cosine theta d theta. So then 0 to pi 8 cosine squared theta minus 4 cosine squared theta d theta. And it's going to be 5 over 2 theta plus 5 over 2 sine theta cosine theta minus sine theta cosine theta, this cosine's cubed, 0 to pi, which will leave you with a 2 pi as a solution. Okay. And I feel like for the one of the first times, I feel like this Lesson is just nothing but examples. All of it. No, like hardly no like other kinds of notes at all. All right. So finding the volume of a double integral, here's our paraboloid. It is going to be above, and it's going to be enclosed, the triangle enclosed by the following lines. And then that's going to give us this image. Okay. So the region D is the following. Gonna try to squeeze it up there. X, Y, 0, X, 1, X, Y to 2 minus X. Okay. And then what you want to do is you want to convert the lines to their polar coordinates. So if you do that, then theta is going to be, you're going to be considering theta pi over 4, theta pi over 2, and then r is going to equal 2 over cosine theta plus sine theta. Okay. So then that's going to give you the following D situation. Not X, it's going to be R comma theta. It's going to be pi over 4 theta pi over 2. And then you're going to have 0 R to 2. Okay. So now if you are converting the equation of the surface, then you're going to have the following volume situation set up. It's going to be R squared times R dr d theta. Oh, pi over 4 to pi over 2. And with R cubed, R to the 4th over 4. Then from 0 to 2 over cosine theta, sine theta, d theta. And then it gets really gross, so you end up with 1/4 pi over 4 pi over 2. Going to be 2 over cosine theta plus sine theta to the 4th power d theta. And then 16 over 4 pi over 4 pi over 2. 1 over cosine theta plus sine theta d theta. Oh, this one's super long, so we're probably going to end up having to go on to another slide. So then you have 4 pi over 4 pi over 2. And that's kind of where we're going to have to leave it. So as you can see, this integral is very complicated. So instead of evaluating this double integral in rectangular coordinates, well, instead of continuing it like this, we're going to now switch back to rectangular coordinates is what they're trying to tell you there. So let's do that. Zero to 1, and then x 2 minus x squared plus y squared dy dx. So now if we evaluate this, we should have a nice situation. 0 to 1. And then x squared y plus y cubed over 3. And that's going to be going from x to 2 minus x dx. Will be 0 to 1. 8 over 3 minus 4x plus 4x squared minus 8 thirds x cubed dx. Then we get 8 thirds x minus 2x squared plus 4x cubed over 3 minus 2x to the 4th over 3, 0 to 1, which is going to give you a final answer of 4 thirds. Now, you may be wondering if someone would have continued along in the polar situation, what would have happened? In theory, you should end up with the 4 over 3. However, I don't think that looks like anything any of us wants to deal with, so I would recommend sticking rectangular. Okay. All right. Don't we know it, but it's another example. This one's a lot nicer. All right, it says finding a volume using a double integral. Use the polar coordinates to find a volume inside the cone and above the xy plane. So what we need to take a look at is that we need to note that if we were to find the volume of an arbitrary cone with a radius a units and height h units, then the equation of the cone would be the following. So like just kind of like, I guess, think of it as a, I don't know, a brain thought. Okay, that's brain and not Brian. What you're gonna have is like if we just assign a as the radius and h as the height, then we would have the following as our equation: the h minus h over a square root of x squared plus y squared. So what that's kind of doing is I don't mind continuing along this train of thought, but I don't feel like it's helping us at all with this problem. All right, we'll keep going. So then that's telling us that we would have 0 to 2 pi, 0 to a, and it's going to be h minus h over a r dr d theta. So if you continue doing what we're used to doing, you're going to end up getting 1/3 pi a squared h as your volume. Again, if you want to dive into this deeper, go free. I realize I'm sick, but I don't think I'm sick enough to not realize that really didn't give us an answer, but that's what it has, so we'll go with it. All right, so finding an area using a double integral in polar coordinates, evaluate the area bounded by the following curve. So using symmetry, we can see that we need to find an area of 1 petal and then multiply it by 8. So here's why we say this. And if you guys haven't seen this stuff before, they're so cool. They're super cute. Probably one of like the coolest things to do. These polar coordinates and polar graphs are just so much fun. So you want to notice that the values of theta for which the graph passes through the origin are the zeros of the function cosine for theta. And then these are odd multiples of pi over 8. So therefore, one of the petals corresponding to the values of theta in the interval. So this is between negative pi over 8 and pi over 8. Therefore, the area bounded by the curve is going to be area equal to 8 because you have 8 petals. And negative pi over 8 to pi over 8. And then 0 to cosine for theta. 1 r dr d theta. And then you have 8 negative pi over 8 pi over 8 1/2 r squared 0 cosine 4 theta d theta 8 on the outside again. So you're going to get 8 times pi over 16, which is going to give you an answer of pi over 2. But moving and grooving. Okay, finding the area between two polar curves. Find the area enclosed by the following. Oops. Okay. So we can see from the symmetry of the graph that we need to find the points of intersection. Setting the two equations will give us that. So you're going to set them equal to each other. I'll try to just do it right here. And then what you're going to find out is that one of the points you're going to have theta equal to pi over 3. The area above the polar axis consists of two parts, with one part being defined by the cardioid from 0, theta equal to 0, to theta equal to pi over 3, and the other part is defined by the circle from theta equal to pi over 3 to theta equal to pi over 2. By symmetry, the total area is twice the area above the polar axis, so therefore we would have A equal to 2, and then times 0 pi over 3, and then 0 to 1 plus cosine theta, 1 r dr d theta, plus pi over 3 pi over 2, 0, 3 cosine theta, 1 r dr d theta. Okay, so you got two parts there that we're dealing with. Evaluating each piece separately, we're going to find that the area is, so you guys know how to do this at this point. Go through, do all the steps. What you're going to end up finding is that A is equal to 2 times 1/4 pi plus 9 over 16 square root of 3 plus 8/3 pi minus 9/16 square root of 3. So if you get rid of that stuff, you're going to end up with 2 times 5/8 pi, which is just 5/4 pi units squared, because it's an area. All right. Last example for this part, and then we'll see how long the next section is. All right, so we're going to evaluate the following. This is an improper integral because we are integrating over an unbounded region r squared. So improper integral because unbounded region r squared. In polar coordinates, the entire plane r squared can be seen as 0, theta, 0 to pi, comma, 0, r, and then it's infinity. Using the changes of variables from rectangular coordinates to polar coordinates, we're going to get the following. So, in other words, we're going to rewrite that. It's going to be from 0 to 2 pi. And then from 0 to infinity, e to the negative 10 r squared. And then r dr d theta. So 0 to 2 pi, 0 to infinity. The limit as a approaches infinity, e to negative 10 r squared, r dr theta. We're going to split 0 to 2 pi, d theta, 0. Well, the limit's going to come out. The limit a approaches infinity, 0 to infinity, or 0 to a rather at this point. 0 to a. And yeah. Okay, so we're going to bring 2 pi. So that's going to just give us pi over 10. All right.